Welcome to our review on radiation around us. First thing to remember then is that we're all exposed to a certain amount of radiation every day from these background sources. And in the pie chart there we can see these different background sources of radiation and the approximate percentage that make it up. So by far the biggest contributor is the radon gas, which comes from rocks, making up 50% of our total background radiation. We can then come down to our medical uses at 14%, as well as the ground in our buildings, which is 14%. If we're looking at food and drink, that's 11.5%. Our cosmic rays is 10%. And then the other things that you probably think are going to contribute a lot more, things like the nuclear power stations and so on, you can see they're very, very small, with only 0.1% for nuclear power, 0.2% for our nuclear weapons tests, and then 0.2% for other things. When you think about your exposure to background radiation, everyone's going to have a slightly different exposure based on the way they live their lives. So where you live will affect it, the nature of your job would affect it, and certain things like your life choices. So if you were to do more extreme sports that mean you break more bones and therefore have more x-rays, obviously your background radiation exposure is going to be higher than someone who doesn't do those things. First use of our radiation then is in smoke alarms. Now our smoke alarms actually use a source of alpha radiation. When the smoke actually enters the alarm, what it does is it stops those alpha particles from ionising the air, and as soon as those alpha particles are no longer able to ionise the air, we see a drop in current through the circuit and then the alarm will sound. So obviously normally what's happening is the alpha particles are ionising the air around it, we've got a current flowing through our circuit so the alarm stays quiet. Because alpha particles are blocked so easily, when smoke is present, that blocks the alpha particles, the air isn't ionised, the current drops and the alarm will sound. The second use of our radiation is to detect leaks. So what we have are miles and miles of pipeline running through the country underground which carries a variety of different fluids. Now if there is a leak somewhere in that pipeline, obviously we know that there's a problem because the amount of fluid we get at the other end decreases. However, we don't know where the problem is. No one would be very happy if we started digging up miles upon miles of pipeline just to see where the problem was. So what we actually do is we mix in a source of radiation to the fluid that's flowing through that pipe, and then if there is a problem, what we can do is, using a radiation detector on the surface, we will be able to work out where the leak or blockage actually is, because the activity after that leak is going to decrease. That then means we've identified where to dig, and we will then minimise the disruption. Obviously this has to emit gamma radiation because we're talking about a source that's got to be able to go through the pipe, the ground and reach the surface. Alpha and beta particles obviously would not penetrate far enough to be detected by the detector on the surface. One other thing we can actually use radioactive decay for is to identify the age of different materials through this process called radioactive dating. So what we actually do is, if our object was once living, we can measure the amount of carbon in the object and then compare that to obviously the amounts we'd expect for different periods of time based on the radioactive decay. And from that we will get an estimated age of our sample. The other thing we can actually date using this radioactive decay are rocks. So what we're actually looking at when we're dating rocks is the ratio of uranium atoms to lead atoms. Because what we find is, as rock ages, the uranium is going to decay and end up being changed into lead. So what we find is that the older the rock is, the lower the ratio of uranium to lead.